Okay, we're going to do some uh, part two questions from our practice Regents exam. And let's start right off the bat with 51 through 53. We'll read the question. It says, the scale diagram below represents two forces acting concurrently at point P. The magnitude of force A is 32 newtons. The magnitude of force B is 20 newtons. The angle between the directions of force A and force B is 120 degrees. Okay. Determine the linear scale used in the diagram. If we go down to the diagram, to find our scale, we want to know what 1 centimeter equals. So we have to figure out the length of these. We'll use our ruler, measure from the very tip of one of the vectors to the tail of it. And if you measured this vector, you would get that it is 8 centimeters long. If you measured the 20 Newton force, you would get that it is 5 centimeters long. In both of those cases, hopefully you can just do this with a little bit of mental math, especially the 20 newtons at 5 centimeters. But if not, you can always just um, set up a proportion or realize that you're doing this division. You're going to see that um, 32 newtons for every 8 centimeters would mean that we would have how many newtons for 1 centimeter? And so this proportion helps us get our answer really quickly. And we see that when we divide 32 by 8, we get 4 newtons per 1 centimeter. And so that's our answer. There's our scale. Okay, great. Let me get rid of some of this so that we can do 52. And it says, on the diagram in your answer booklet, use a protractor and a ruler to construct a scaled vector to represent the resultant of forces A and B. Label the vector R. Okay, so let's go into that. Let's look. To do this, there's a few ways you can do it. One easy way is to just, all right, this 32 Newton force is straight up. It's pretty easy to use our ruler and just make a perfectly vertical line. And so since we know that's 8 centimeters, if we go over here and draw a line straight up, I should use my ruler. So let's make this a straighter line. And I make it exactly the same length as our initial vector. There it is. Here is vector B down here at the bottom, right? And then the blue arrow that I just redrew here, that's vector A. And so it's B plus A. Here is our resultant. And so it's okay if you have, some other lines in here as long as your actual resultant is labeled R. Make sure you label it R so you get full credit for this answer, right? If you didn't have anything labeled and you have both this blue vector and the black one, the grader will not know which one you think is the resultant. And so now let's go back and relabel this R. So there's our resultant. Now, go to question 53. Determine the magnitude of the resultant force. Okay, the magnitude of this resultant force. A lot of people are trying to use Pythagorean theorem. And the bottom edge, the purple vector, is 20 newtons. This vertical is 32 newtons, right? And that's true, but this can't use Pythagorean theorem. Why? Because this triangle that we have here is not a right triangle. So we have to do it some other way. So how are we going to find the resultant? We're going to have to measure this, okay? And once you've drawn your resultant vector, you're going to have to measure exactly from the tip of your resultant to the tail. So give me a moment, I'll get my ruler out, measure that. And we get that it is exactly 7 centimeters long. And so if it's 7 centimeters long, we know that every centimeter is 4. That means that our resultant is 28. I don't have the blank for 53, so let's just throw that down here. 53 has a blank line and newtons here because they're giving you your units, and all you would have to say is 28 because that's 7 centimeters times 4 gives us 28 newtons. So there we go. That's our first set of questions. Let's move on to the next one. Base your answers on 54 through 56 and the information in the diagram below. Okay. A student pushes a box weighing 50 newtons 6 meters up an incline at a constant speed by applying a force of 25 newtons parallel to the incline. Okay. The top of the incline is 2 meters higher than the bottom. So lots of information in there. After I read the question, I'm actually going to take a lot of that information, break it down, put it into the diagram if it's not already there. So 54 and 55, it's one question. Remember those 54, 55, they're showing that because this is a 2-point question, which means you have to show all work, including an equation and substitution with units. So this says calculate the total work done on the box by the student when pushing the box from the bottom of to the top of the incline. All right, so when we're pushing with a force, work can be found by multiplying our force times the displacement. And so there's our formula. Now we have to substitute with units, so we don't have anything to substitute for work. That's what the question is asking us for. The force that we've applied, they actually have it in our picture already. So this force is 25 newtons. There it is. And the displacement is already in the diagram as well. It's gone 6 meters. And because the force is parallel to that displacement, we can just multiply those two things together. So 6 meters times 25, we get 150 joules. There it is. Don't forget that work is energy. And since work is energy, it has the unit of joules. Okay, you do need that. And some people forget, oh, I don't know what the units are. How do I get full credit without losing a point for joules? Here's a little trick. Joules is the best unit to use for this, but you will still get full credit if you just use the units that were in the previous step. So a joule is actually equal to a Newton meter. Okay, and if you used newtons times meters, because that's what the operation was on top, newtons times meters, this would give you full credit for your units, and you wouldn't lose that point if you forgot that work is measured in joules. So that's something really good to always remember. Okay, the next part. Describe what would happen to the total work done on the box by the student to push the box 6 meters up an incline at a constant speed if the coefficient of kinetic friction between the box and the incline were increased. Okay, so I didn't even really talk about this idea of constant speed. Don't forget, constant speed means that we have a net force of 0, right? It's equilibrium. Net force is 0, which means that applied force is exactly equal to friction. So force of friction here would definitely be 25 newtons. Now in this problem, if we increase the coefficient of kinetic friction, right? If that goes up, then friction gets bigger. So in order for us to continue to push at a constant speed, we would have to push harder. And so we're applying more force, still moving the same distance. And that means that our total work would increase. You don't need a full sentence. It says describe what would happen to the total work. Really, increases would give you full credit. I'm going to write total work increases because I think that's just a better answer. But increases is all you need. Total work increases. There we go. All right, let's go on to the next one. 57. In the diagram below, a light ray is incident on the interface between the glass and the air. When the light strikes the glass-air interface, some light is reflected. Okay, careful with this, reflected. On the diagram in your answer booklet, use a protractor and a straight edge to construct the reflected light ray. And so this one's a nice, easy one. It's going to be reflected, and when we have reflection, our angle is exactly equal. So I should be using a protractor, measuring theta r, which is our theta I, which is our incident angle, and this theta r, which is our reflected angle, will be exactly equal to that incident angle. So these will be exactly equal, and that's all you have to do. Now, does some light get through? Yeah, absolutely. And you should understand that. And other questions on previous years have had you show that transmitted light, and using Snell's law, you should see how much it bends, right? As we come into air, we will actually bend towards the normal line. So instead of continuing in a straight line, it bends closer to the normal line. Again, not necessary for this problem, but you should understand how to do that. So think about that. Make sure you understand it. If you don't, make sure you find a Snell's law practice problem. But making sure you read this is a lot less work than Snell's law, and you get to just do it quick, move on to the next question. So let's go. All right, we're on 5859. The current in a wire is 5 amps. Calculate the total amount of charge in coulombs that travels through the wire in 36 seconds. And so you just have to know what current is and how current is charge. This is what they're asking us for. Q, that's what we need for our answer. And it's current equals change in Q over T. And so there's our, remember this is a two-part question, so I wrote my equation. 5 amps for current equals, we don't know our charge, and our time is 36 seconds. There we go. I just did substitution with units. I just got +1 for this question. So I got half my points already. Last step, we take 5, multiply it by 36. If we cross multiply this, let me show you. So delta Q is 180. Now, what are our units? It tells us coulombs. So use that as a resource. Don't forget your units. I just got my second point, +1. All right. Next question. 6061. A spring with a spring constant of 100 newtons per meter possesses 2 joules of elastic potential energy when compressed. Calculate the spring's change in length from its incompressed length. Okay, 2-point question. This is really last two, this previous one and this one. These are what I call plug and chugs. Just find the right equation and put in your numbers, and you got your answer. These are gimme questions. Spring with a spring constant of 100 newtons per meter. This is K. Possesses 2 joules of potential energy, and it's elastic potential energy. Okay, so make sure you realize that, right? Potential energy of a spring. And then they're asking us the spring's change in length. On our reference table, change in length is represented with an X, because if you find that spring potential energy or elastic potential energy, it's 1/2 kx squared. And that's what we're looking for. We're looking for the x in that equation. And so that's our equation. Let's substitute our units with units. This is 2 joules equals 1/2 times 100. Don't forget the units that go with that 100. It's not just newtons, it's newtons per meter. And then we're going to have our x squared here. Okay, so now you can do everything on your calculator. You don't have to show any additional work. I'm going to show a little work because I think it's helpful to avoid mistakes of typing things in your calculator and trying to do some mental math. So I'm just going to rewrite 2/2 of 100, that's 50, x squared. Notice I don't have any more units. Divide both sides by 50. Okay, and then I have to take square root of both sides. So 2 divided by 50. And then I take my square root. And this comes out to be x equals 0.2 meters. And there's our answer. Let's go on to the next one. It's like looks like my questions disappeared. We're having a little, see if I open it again. Here we go. Okay. 6465. An argon ion laser emits blue-green light having a wavelength of 488 nanometers in a vacuum. Calculate the energy of this photon. Okay, so what do we have to do? We have to remember energy of a photon is right on our reference table, and its energy of photon equals h times f. Okay, and I'm pulling up my reference table really quick because I need h. H is a constant. It's on the front page, and energy of a photon equals 6.63 times 10 to the negative 34, and this is joule times seconds. You don't have to memorize that. It's right there. Don't forget the units because this is a show will work 2-point question. And then frequency, we don't have it. So I'm stuck. I can't answer this. But when we look at the reference table, our energy of a photon has a second part of the equation. Energy of a photon can also be written as hc over wavelength. And now that's the part of the equation that I need. So I didn't have to write this out originally. I just wanted to show you sometimes you find these dead ends and you're like, oh no, I'm stuck. I can't answer the question. You actually can answer the questions because this, you just hit a dead end. You got to find a new approach. This is our wavelength. And so now we have everything we need because h is a constant and so is c. C is the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. Okay. And then it's all divided by our wavelength. Here's the tricky part though. This is nanometers. So 488 nanometers, I'm going to kind of write this a little weird because nano has to be converted into just plain old meters. So this nano, we look it up on our reference table, and nano is times 10 to the 9th. So we can get rid of nano and just say it's times 10 to the negative 9. This is on the front page of our reference table, the bottom corner. And so now we have meters. Now, why do we have to convert meters? Some problems every once in a while, like you didn't have to convert meters. I know we've done a few like that. But I always suggest converting to meters. In this case, we must convert to meters because there are meters in other parts of our problem. In other constants, meters are built in. And so you'll have a mismatch of units if you don't make that conversion. Okay, and so now we got a little bit of calculator work. Let's pull up our calculator. We can do this together. So we have 6.63, and then we're using the second EE button to put our 10 to the negative 34 times 3 second EE 10 to the 8th, and then we're going to be dividing by 488 second EE negative 9. And I have all my numbers in. I just hit enter, and we get the energy of this photon is equal to 4.08 times 10 to the negative 19 joules. And there's our answer. So a little bit tricky making sure we do our unit conversion, but otherwise pretty straightforward problem as long as you use that correct part of that photon energy equation. All right, let's go to the next question. Question 66 through 70. All right. So let's read. It says, an incandescent light bulb uses a length of thin tungsten wire as a filament. And they're making sure you know what a filament is. It's the part of the operating light bulb that produces light. And they even give you a little diagram and show you that filament. In one particular light bulb has a 0.22 meter length of tungsten wire used as a filament. This tungsten wire filament has a resistance of 19 ohms at a temperature of 20 degrees. The tungsten wire filament has a resistance of 240 ohms when the bulb is operated at a potential difference of 120 volts. Calculate the cross-sectional area of this tungsten wire filament. Okay, show will work. So cross-sectional area in relation to resistance is a formula that we have. First off, let me just remind you what it means. This little wire that's here, inside here, it has some cross-sectional area. It's very small. It's a teeny tiny wire, but if you were able to measure the area of the end of that. That's what they're asking us for. And so the resistance equals rho L over A. Okay. And you got to know what all parts of this are. And the problem that a lot of people have is they give two resistances. And so we're not really sure what to put for R yet. Let's keep going. Well, resistivity, that's something that's on our reference table. Resistivity. And when we look up resistivity, the resistivity for tungsten is 5.6 times 10 to the negative 8. And in the chart, it doesn't have the units, but if you look at the top of the column, that's ohm meters. So that's our resistivity. That's this guy. Put parentheses on it. The length is 0.22 meters. They gave us that. And we're looking for area. So I still don't know what for my resistance. But when we look at that resistivity chart, all resistivities that they give us are given for 20 degrees Celsius. So this is at 20 degrees Celsius. And so we're going to need the resistance that goes along with that 20 degrees Celsius, because that resistivity will go up as it gets warmer and warmer. And so this is 19 ohms. And now we just have some numbers and a little bit of algebra to do to solve for A. So let's plug some of these in. I am going to multiply my 5.6 second EE negative 8 times 0.22. Okay. And then after I'd cross multiply, I'm doing some of this in my head, and that would be full credit still. I would have to divide both sides by 19. And so I'm going to take that answer I just got on my calculator and divide it by 19, and hit enter. And we get that our cross-sectional area is equal to 6.48 10 to the negative 10. And this is meters squared. Don't forget area. Just like in your math classes, you know what area is. It's got to be square units. And since we're measuring everything in meters, this is meters squared. Okay, let's look at the next part. Express why the resistance of the tungsten wire filament increases when the bulb is being operated compared to the resistance of the filament at 20 degrees. The answer is because resistivity increases with temperature. Okay, and that's enough. Now, some people are like, well, do I have to explain why it increases with temperature, that the molecules are vibrating more? That would be great, but not necessary for full points on the question. All right, question 6970. Calculate the power of this light bulb when it's being operated at a potential difference of 120 volts. So, power. We got a formula for power. Power equals, now we've got a lot of parts. A lot of people go straight for VI, right? That's the one we use most of the time. But when we read this, we don't have I. So it's not really a good strategy. So let's look at some of our other equations that we can use for power. The next part of this equation is I squared R. Again, we don't have I, so that doesn't help us. And then we have V squared over R. So you don't have to write this whole thing out, but I'm just writing it, so we can talk about it. We want to know power, and we have V and R. So I wouldn't write all that. I would just say power equals V squared over R, and then we can plug in our numbers. So we're looking for power. We know the problem told us we're dealing at 120 volts. Don't forget to square it. That's a common mistake. People forget this squared. And then we're dividing. Now, we have to think about which resistance are we dividing by? They were giving us two of them. Previously, we used the 19 ohms because it was at 20 degrees. Now, we're actually operating the light bulb. If 120 volts are going through it, it's heating up. If it's heating up, it's at this higher resistance. So when it's at 120 volts, 240 ohms are your resistance, okay? And so, again, calculator work. Let's pull up our calculator. We've got 120 squared divided by 240, and we get power equals 60. Now, again, some people forget what power is. Hopefully you remember. But if you don't, what can we do? Well, we can look at the units here, and our units are V squared over ohms. That would give you full credit. I wouldn't do that. That most people might forget that the V ends up being squared and your units have to be squared. But if you're totally drawing a blank, try and figure it out from the numbers you plugged into the equation. But we all know power is measured in watts, and capital W for watts. Great, let's move on. 71 through 75. 120 Newton force applied to a wooden crate at an angle of 30 degrees above the horizontal causes the crate to travel at a constant velocity across a horizontal wooden floor, as represented below. Calculate the magnitude of the horizontal component of the 150 Newton force. Show will work, including equation and substitution with units. Okay, so what are they talking about? Horizontal force. We've got this 150 newtons, but only some of that force is pulling sideways. So this is our force in our x direction. Okay, that's what they're asking us for. The word horizontal component of force is this blue arrow that I've just drawn. Okay, and hopefully you remember how to draw these. That arrow should be straight below the point of my 150. So if I went straight down, that's how long the blue arrow should be. And hopefully you can see now there's a right triangle there. That right triangle is the reason we get to use trig. And if you look up on your reference table, there's an equation for horizontal component of a vector. Okay. On the reference table, I'm going to write it over here. They say ax equals a cosine theta. I'm not going to put the a's in. If you wrote that, you get full credit for showing your equation. I'm going to write it as a force. So force in the x equals force cosine theta. Okay. And now our force in the x is what they're asking us for is 150 newtons cosine 30 degrees. Now, whenever you're doing calculations with cosines and sines, you have to make sure you're in the right mode. People ask the question, is it radians or degrees? You should know the answer to that because the only thing that indicates if it's radians or degrees depends on how we're measuring our angles. And we know how we're measuring our angles. We're measuring them in degrees. And so we're going to be in degree mode. So we plug in our calculator in degree mode, 150 cosine 30. Hit enter, and we get our x component equals 129.9 newtons. And that's our answer. Make sure you have your newtons because it's still part of a force. And so it's a force still. Components of forces are forces. Determine the magnitude of the frictional force acting on the crate. Now, most people, when they see frictional force, they jump straight to the friction formula. Friction is mu Fn. And then, okay, we've got wood crate, wood floor, and we need to know the normal force. Now, the normal force is hard to find out. Why? Well, they didn't tell us the weight of the box. Not to mention that we're pulling up on the crate, so we're lifting it off the floor a little bit. So even if we knew the weight, the normal force is going to be a little less than the weight. So we're kind of stuck right now. We don't know this normal force. So how are we supposed to get friction? And there's a hidden part to this problem, what I call a hidden given, right? And then we mentioned it a little bit earlier. It's going at a constant velocity. The words constant velocity should tell you something really important. You get bells and whistles in your head when you read constant velocity. Constant velocity is equilibrium. Constant velocity, besides meaning equilibrium, means, well, we're not accelerating, right? And if we're not accelerating, that means that our net force is zero. Okay, all of these things are true. And so when I look at this, well, what do I have? I have a wooden crate. It has a weight, Fg. That Fg is canceled out by the normal force, right, which is up. But not only that, there's also this upward component. I'm going to do it in orange, force in the y. So force in the y plus this force in the y plus this upward normal force, I should label that Fn, those two add together to cancel out gravity. Okay? Gravity gets canceled by them. Gravity is canceled by those two. Okay, so that takes care of equilibrium in the y direction. But if we're moving at a constant velocity, there's also equilibrium in the x direction. And so friction is pulling against our motion. And if friction is pulling this way and we're in equilibrium, the only two forces that we have in the x are friction and the x component. So they have to be equal. That's the only way they would cancel each other out perfectly and allow us to be in equilibrium. And so the answer to this is just whatever you got on 7172. So in this case, 129.9. Now, if you calculated this first part wrong, let's say you didn't know how to do it and you just put that, oh, the x component is 10 newtons. If you put 10 newtons down here, as long as that matched your previous part, you get full credit. Okay, so don't worry about if you get problems wrong, don't skip them. Try and write some sort of answer if you need it later on so that you can get full credit for the next part. Okay. Even if you had no idea how to do this 71, 72, make up a force. Force, the x component is, I don't know, 10. Make it a nice easy number if you're making something up. All right, so now we just figured out the component of friction, and now 7475 says calculate the magnitude of the normal force exerted by the floor on the crate. And so to do that, all right, well, the normal force is in this equation, and we have everything now because we have force of friction. We just figured it out with our free body diagram. We know the coefficient of kinetic friction. I'm going to put a little k here to remind us it's kinetic because we're moving. And then we can solve the normal force. So 129.9 newtons equals, we go onto our reference table and we look up the coefficient of kinetic friction for wood on wood, which is 0.3. No units needed because coefficients of friction have no units. And then solve for Fn. And so we divide both sides. Again, showing this division in your work is not necessary, but I like to do it so I don't make any silly mistakes. And then I throw that into my calculator. So I still have my 129.9. I'm not going to rewrite it. I have it there. If I just use that, then I don't get any rounding errors, right? So I'm just going to take that, hit my divide button. So it says ANS, the previous line's answer, with no rounding, divided by 0.3. And here we are. Our normal force is 433.01 newtons. We got our normal force. And we got both points. Equation, substitution with units, answer, 2 points. All right, let's go to the next one. On a flat level road, a 1,500 kilogram car travels around a curve having a constant radius of 45 meters. The centripetal acceleration of the car has a constant magnitude of 3.2 meters per second squared. Calculate the car's speed as it travels around the curve. Okay, so to be honest, I'm going to draw a little picture. If I was doing this on scrap work, maybe I would do it on my scrap paper. Maybe I'd do it over on the side. I know it's just me thinking about the problem. You can do it in your answer booklet. Just watch out you don't use up all your space. So I'm going to think about my car traveling in a circle. So let's put a circle down. And we know the radius is 45 meters. We've got our car, 1,500 kilograms. Here's our car. Put on little tires. This is an overhead view. Okay. And now they tell us the centripetal acceleration. Centripetal acceleration we know is pointed towards the center of the circle, AC. And now they're asking us for the speed. So let's go through. Let's identify. We got a mass here. We've got a centripetal acceleration, AC. What else did they give us? They gave us a radius. Let's do that in blue. I put it in my drawing, R. And we're looking for speed, okay, which is V. And so with all this stuff, hopefully you remember that centripetal acceleration is equal to V squared over R. There's our equation. We plug in AC is 3.2 meters per second squared. Velocity is what we don't know. The radius is 45 meters. And we're going to need to cross multiply to solve this. Put this over 1. And again, I'm going to plug in my calculator. 3.2 times 45. And so I get 144 equals, well, this is V squared times 1. So that's V squared. That's not my answer. We got to take our square root. Take our square root of both sides. They made it nice and easy. That our number is a perfect square. 12 meters per second is our velocity. It doesn't have to be a perfect square, but in this case it is. So now let's look at 78. Determine the magnitude of centripetal force acting on the car as it travels around the curve. And so centripetal force, Fc, equals MAC. And so we have our AC given in the problem. And so this is just going to be force equal to the 1500 times that AC, which was 3.2. Grab our calculator, throw those two in. Notice I'm not showing any substitution with units. I don't even need to write that. I'm just showing it. We could just plug this into our calculator. 1 point question. And we get 4,800 newtons. Now, 79 says what force provides the centripetal force needed for the car to travel around the curve. This is friction, right? Friction is acting sideways. And that's where we need the force to be. It's towards the center of the circle. Some people have said gravity and things like that. Gravity is pointed down, not towards the center of our circle, so that doesn't work. And you can kind of remember this because you can't make a turn when you hit a patch of ice. If you're trying to turn and you hit ice, you'll skid and hit, continue to travel in the straight direction that you were going. You need friction in order to make a turn. Okay, and 80 says, describe what happens to the magnitude of the centripetal force on the car as it travels around the curve if the speed of the car decreases. So as speed goes down, you can I'm going to rewrite our AC calculation. AC is V squared over R. So if this top number gets smaller, then AC also gets smaller, right? And if that gets smaller, we would see that our calculation for force gets smaller. And so describe what happens to the magnitude of centripetal force. I could say centripetal force decreases. All right, move on. Our last section of questions. This is 81 through 85. They're showing us a guitar. A musician plucks a 0.62 meter long string on an acoustic guitar as represented in the diagram below. Okay. The plucked string vibrates to produce a musical note called G. The waves traveling along the vibrating spring produce a standing wave with a frequency of 196 hertz. On the diagram of the standing wave in your answer booklet, label one node with the letter N and one antinode with the letter A. And so here is our node. Nodes have no motion. That was one. Here's the other. We don't have to label both. So I'm just labeling one. And our antinode is right in the middle. So I just put an A right there in the middle. Okay. 82. Determine the wavelength of the standing wave on the 0.62 meter long vibrating string. And it's a little hard to see in this, but like this curve, very gradual, but I'm going to exaggerate it more, is only half of maybe a sine curve. And so to get your full wave, you have to have the bottom half as well. And so you'd have to double the 0.62. And so this ends up being 1.24 for our wavelength, because that would be 2 times the length they showed before. All right. 8384, calculate the speed of the wave traveling on the vibrating string. And so speed of waves, maybe you think v equals distance divided by time. That could work sometimes if they give you information about distance and time, right? That's our standard speed calculation. But specific to waves, we can rewrite this formula as v equals frequency times wavelength. Again, this works sometimes, but we don't have anything really about time right now, so we're going to throw that one out. Okay, and do we know the frequency? Sure, they gave it to us in the problem. So our frequency, I should put this over here on the left. Let me move it over. Okay, that's the formula we need. Our velocity is what, or speed is what we're looking for. 196 hertz. And then wavelength. So notice, wavelength is used in this calculation. If you had no idea how to do 82, you were like, hey, I have nothing here, it's blank. Make something up so that you have a number that you can plug in for the next question. Don't just get both of them wrong because you weren't able to answer 82. Make up a number. I'd say 1 meter. Why not? 1 is a nice, easy number for a calculation. So make up an answer if you have to, so you can get full credit on the next part of the question if you're totally lost. I think you can make a better educated guess than just randomly guessing 1 meter. But again, sometimes we draw a blank, and don't just skip everything after the part where you hit a roadblock. And so we'll take our 1.24 times 196, and we get a speed of 243.04 meters per second. And there we go. Got our answer. Last question. Describe what happens to the frequency when the musician shortens the vibrating portion of the string by pinching the string against the fretboard while the string continues to vibrate. And so the frequency, okay, we have to say if it goes up or goes down or doesn't change, right? What happens to it? If you know anything about music, if you've ever plucked the string on a guitar, you might already know this. As your finger shortens that string, right, the pitch goes up. So that's why small instruments like flutes make high pitch sounds, and big instruments make low sounds like tubas. And so shorter string here would be a higher pitch, which is a higher frequency. So you can kind of answer that without even knowing about the physics. Let's do the physics part of this. Shorter string means that our wavelength, this number, goes down. But velocity cannot change. The velocity is a factor of the string, and the string is not changing. So this number, this V, doesn't change. So if the 1.2 goes down, the frequency must go up so that V remains unchanged. So you could do it mathematically as well, but I think just your intuition about what happens on a musical instrument when you shorten the string should help. So the frequency increases. There we go. All done. So hopefully that helps answer some questions on this. Continue to study, keep practicing, and good luck on the Regents exam.